we discuss about the work done or the constant force. In that condition, we calculate this work done, their condition, different cases, or the constant force. There are many in the daily life. There are many condition situations with our varying force, or there will be the force which is applied force which is not a constant. So to calculate this work done, we are considering one example. We are taking here the spring which is their one end will be fixed to any wall and second end which is attached to one block. So our condition is simply we are considering the wall, and here we are considering the small spring which one end is fixed to that wall. One end which is fixed to that wall, and another end of that spring which is tied with some block. Okay, so here we can see the spring which is having the spring constant K. Here the spring which is having the spring constant K, this is origin. So this spring which is there one end which is tied to the wall, second end which is tied to that block. Here we can see that we can defining the positions. This I can mention this point A which is nothing but at the rest condition or a natural thing. In that natural condition, spring is in the natural condition. This A point or this block at x is equal to 0, or this block will be at the rest condition. Now we are considering if you applying the force, or simply you know that we are considering this spring also in that same condition. There one end will be the fixed, second end will be tied with that block. This is your natural condition. In that natural condition, x is equal to 0. This block at the position x is equal to 0. And in that conditions, you know that if you one more thing about that spring constant. If this K is a spring constant, then the force on that block, if this K is a spring constant, and then the force on that spring or block which is K time elongation of that spring. Here in your natural condition, this spring or this block at the rest condition. Now if you apply the force, you apply the force, this block will be displaced or changing their position from x is equal to 0 to x is equal to x1. So we just extend this. If this force is very small and the displacement or this block will be cover the distance small, infinitesimally small, then we can say that, or I'm just draw here. Okay, we are simply making us very small. This is our A point, and we are displaying or we are changing only small distance. So from this point A to A dash, this is A dash. So in that condition, this body or this block displaced with a small distance ds. This is dx. So in that condition, if you are applying the small force or any force to that block, this block will be moved or displaced with a small infinitesimal small distance which is nothing but dx. Or if you apply the force, these blocks move from your x is equal to 0 to point x is equal to x1. You are applying this force. If you apply the force, these blocks again move, and which is at x is equal to x1, which is nothing but this is position B and point x is equal to x1. In the same manner, in the first condition, where apply the small force, or apply the force, this block will be displaced with the displacement or distance dx. And in continue that, we are applying force, this will be displaced from dx, from here, any small points up to that point B, which is nothing but x is equal to x1. So, in that condition, this block will be covered or displaced with distance x from point A to point B, which is nothing but this block will be displaced with distance x. Now, again, if you apply the force, again, this varying force, then this block will be moved from x1 to x2. Again, any more we are extending here, and from point C, x is equal to x2. Where apply the force, body or that block will be moved from x is equal to 0 to x is equal to x1. From x1 to x2. Here, in your first condition, when this block will be displaced with a small distance dx, in that condition, the work done in your first condition, which will block move from A to A dash with a distance dx, this work done which is equal to f into dx. This work done is nothing but f into dx. With application or with that applied force, this block will be moving with a distance dx, as this force and this displacement, are opposite in directions. Here we can see that if you considering this spring, which is one end is at the fixed to that wall, another end which is tied with that block, and if you are applying that force, this body, this spring will be displaced or this block will be displaced in that condition. If this spring will be or this force in the earlier point we can see, or at the beginning we can see that this spring constant K. If this spring constant K, then this force on that block, which is K times elongation of the spring. We have already discussed that point, which is if this K is the spring constant, if this K is a spring constant, then the force on that block, which is K times elongation of that spring. Okay, now we are coming to our this first point. So our dW is equal to F into dx. Applying force into that displacement, in that conditions, this force and displacement. Here, this we are applying the force and the displacement. This is nothing but the displacement, and at that condition, this applying force which is opposite to each other. Here, force and displacement which is opposite to each other, it means that theta is equal to 180, or we can say that phi, and it is a dot product. In that condition we can say that this dW, which is nothing but negative f dot dx, it is. So this negative sign indicate that this force and displacement in that spring constant, which is one block which is tied to that block, in that condition, this force and the displacement or this in that elongation, when this block will be displaced, in that condition which are opposite to each other. This negative sign indicated that this force and displacement which are opposite to each other. Okay. Now again one more thing, in the here we are considering the spring with spring constant K, then the force is nothing but F is equal to K times elongation, which is nothing but K times elongation. It means that F is equal to K into X. Here K is equal to X. Now Yeah, we are writing here. We can use this part also. Now we can put this value. This dw is nothing but minus kx into dx. Here we can write or put this value force. The spring force F is equal to k times k is nothing but your spring constant and x which is elongation. So F is equal to k into x. This is a force. We can put this value into your work done. You get dw is equal to minus kx dx. Now we have to calculate the total work done. Here we can calculate the work done of that moving block. So for that condition, in that this moving block from x is equal to 0 to x is equal to x1, from this A point to B point, which is nothing but initial condition is x is equal to 0. The point at the point B, this block will be moved from x to 0 to x is equal to x1. So in that condition we are calculating, determining this work done. So for that condition we can write W is equal to, from x is equal to 0 to x is equal to x1. X is equal to 0 to x is equal to x1. Kx dx. It is nothing but kx dx. This k is constant, we can take outside. K times x is equal to 0 to x is equal to, or and I am writing x 0 to x1, x into dx. We can write x is equal to, w is equal to k times integration 0 to x dx. Okay. From this equation w, is equal to, here we can write what is the integration. So this integration is nothing but you get integration of x dx, which is nothing but 1/2. This is k times, this is the negative sign, minus k. This is minus k 1/2 x square from 0 to x1. From this minus k 1/2 x square, this integration of x dx is nothing but 1/2 x square. Your limit from this block will be moved from x is equal to 0 to x is equal to x1. So you get minus k by 2 x square from x is equal to 0 to x1, or finally you get minus k or 1/2 k x1 square. This w or the work done in that first condition, this block which is moving from x is equal to 0 to x is equal to x1, in that condition you get the work done is nothing but minus 1/2 k x1 square. So similarly you can calculate this. Similarly here you can calculate if this block which moving from x1 to x2, x2 to x3, or up to that final position at the end position. So here you can get if you want to calculate or if you want to determine the work done for any other conditions, if this block which is moving from x is equal to x1, in the first condition block will be moving from x is equal to 0 to x1. We are now considering the block from x1 to x2. From x1 to x is equal to x2. In that condition again your work done you can say from x1 to x2. It means that block which is moving from position B to point C from x is equal to x1 to x is equal to x2. In that condition again our work done which is nothing but minus k. This is minus k integration from x1 to x2 x dx. Simply x dx. We have to solve this integration. You get from w x1 to x2, which is nothing but minus k into 1 half x square. 1 half x square from x1 to x2. You can get this value from work done, total work done from x1 to x2 is nothing but minus 1 half, or k into 1 half x square from x1 to x2. And in that condition, the work done will be, I'm writing here, from x1 to x2, which is nothing but minus 1 half k, and this integration is nothing but x1 square minus x2 square. We can writing this x1 square minus x2 square, or simply 1 half, or we can simply write here minus x2 to x1 from this integration from x2 square minus x1 square. So from this equation we are writing that, which is nothing but minus 1 half k into this x1 x2 square minus x1 square, or simply we can write 1 half k x1 square minus 1 half k x2 square. We can simply write this total work done, which is from x1 to x2, which is equal to 1 half k x1 square minus 1 half k x2 square. So this is condition, this block which is moving from x is equal to x1 to x is equal to x2. If you brought this block again back condition, again their back original position, so we are considering again here this x is equal to x2 to x is equal to x1. We are just simply changing their position. Again, in the first condition, block which is moving from x is equal to x1 to x2. Now we brought this block again their original position, which is x1. So in that condition, from x2 to x1, this is, we can say, x2 to x1. Then your integration change. So integration from x2 to x1. Their integration again changes, which is from x2 to x1, from x2 to x1. And in that condition, the integration is nothing but minus k1 half x square from x2 to x1. Now we are reverse condition. In that reverse condition, your integration will be changing, and the work done from x2 to x2. And finally, you get, I'm writing here directly this work done from x2 to x1, which is nothing but from x2 to x1, which is nothing but 1 half k x2 square minus 1 half k x1 square. Okay, this is your first condition, this is your second. In the first condition, block will be moved from x1 to x2. In the second condition, which is reverse condition, this block will be again at the, which is moving from x2 to x1. In that condition, you get 1 half k x2 square minus 1 half k x1 square. Now, if you considering or simply adding these two equations, if you add both equations, then you get here w x1 to x2 plus w x2 to x1, which is nothing but, we can see, 1 half k x1 square minus 1 half k x2 square plus 1 half k x2 square minus 1 half k x1 square. And here we can check, this plus goes to here, this minus cancel out, you get 0. It means that this is nothing but 0. Again, we can check one more condition. In the work done, we are calculated the work done in that varying force. Here, in all this total example, this force is varying, and in that varying force, if there is round journey or closed loop, this round journey, or we can say that closed loop, again you get the total work done is 0. Here you get the total work done by that system, by that body is 0. Here also you get this round journey, or in the previous example also we can check that this is not depends on the path, not which is only depends on the end points, and your closed loop or round journey, in that condition work done is 0. You can solve or check the conditions. Now in that here also, just like your previous example or previous case, which is for the constant force, there we are solve some cases, check some cases, the if this force and displacement in the same direction in the perpendicular condition. Here also there are some cases, we are check some cases. If this spring, which is maybe a compress, it may be a, if you stretch, what happened to that work done. Now we are checking some conditions. In that condition, various conditions for that spring constant, or for that only the spring, which is here there is a varying force. First we are considering in the spring which is in the natural condition. First condition, the natural spring is in the natural condition. In that condition, this x1 is equal to 0. This, in that natural condition, this block will be at steady state at x is equal to 0, or we can say that x1 is equal to 0. And finally, it will be stretched to the point your x2 is nothing but x1. If you stretch this, so if you apply this force in the first condition at x is equal to 0, if you stretch this spring in that condition, your x2, which is nothing but x. In the first condition x is equal to 0, if you stretch this spring in that condition, x2 is equal to x. Then what is the work done? Now we have to know that. Here I am directly writing W is nothing but in minus kx dx. Okay. In general equation I am writing here W is equal to minus integration of k, or simply again we can simplify, because the k is nothing but the constant, so we can write minus k integration x into dx. Okay. Now we are solving the first condition. We are considering x1 is equal to 0, x2 is equal to x. Then W will be nothing but minus k integration from 0 to x1. This x1 is equal to 0, x2 is equal to x times k into dx. So the total work done will be minus 1/2 kx square. In the first case, initially the spring is natural condition, so x1 is equal to 0. If you stretch this spring, then x2 is equal to x. Then the total work done will be minus 1/2 kx square. Second case, if this spring in the natural condition, if it is in the natural condition similar to first one, again x1 is equal to 0. Now in the second, and finally it is in the compressed state. In the first condition we stretch it. Now in the second case this spring in the compressed state. If it is in the compressed state, then x2 will be minus x. If this displacement, which is nothing but with a negative displacement, so we can say that this x2 is equal to minus x. Again work done is equal to minus k from 0 to minus x from 0 to minus x dx, and you get the total work done. Here you get the total work done, which is nothing but again minus 1/2 kx square. Again you get the same, w is equal to minus 1/2 kx square. This is second condition. Now we check the third condition. This spring which is at the stretch position. In the third condition, this spring in the stretch condition, if it is in the stress condition, then x1 is equal to x. If this spring in the stress condition, then x1 is equal to x, and finally it is in the natural condition. Now in first condition, it is in the first, initially it is in the stress condition, so your x1 is equal to x, and at the final condition it is at the natural state. If it is at the natural state, then x2 is equal to 0. Here x2 is equal to 0. If you know the x1 and x2, you can calculate, you can determine the work done, which is nothing but minus k integration from x to 0, from x to 0. Writing is small. Okay. x2 is equal to 0. So from k minus k times integration x to 0, x into dx, which is nothing but, in the third case you get this integration, which is nothing but 1/2 kx square. Here you get the positive value. This work done is nothing but 1/2 kx square. In that condition, in the third condition, we are say that at the initial condition, this spring at the stretch condition, if it is in the stretch condition, your x1 is equal to x. In the final condition, this spring is at the natural condition. If it is at the natural condition, then x2 is equal to 0. And if x2 is equal to 0, you get the for that integration, this from x1 to x2, x is equal to 0 to x is equal to, sorry, x1 is equal to x1 to x2 is equal to 0. You just calculate this integration, you get 1/2 kx square. Now we are moving our fourth case. We are moving to the fourth case. In that fourth case, initially at the initial condition, this spring in the compressed condition. If this spring in the compressed condition, then your x1 in the fourth condition, initially this spring is the compressed, then x1 is nothing but minus x. This, if it is at the compressed state, then this x1 is nothing but minus x. And finally at the final stage, again it is at the original condition or simply natural condition. If it is at the natural condition, x2 is equal to 0. Now you get x1 and x2. We can calculate w is equal to minus k from minus x to 0 x dx, which is equal to, just calculate that integration, and this integration again become, it is 1/2 kx square. Again you get the work done is nothing but 1/2 kx square. This is your fourth condition. In that fourth condition, initially this spring is in the compressed state, and at the final condition at the natural state, which is nothing but x2 is equal to 0, and you get the total work done 1/2 kx square. Now next condition or next case, which is fifth. In that fifth conditions, we are assuming that, or in the initially spring is in the compressed state. Spring in the compressed state. If it is in the compressed state, x1 is equal to minus x. In that condition, x1 is minus x, and finally this spring in the stretch condition. initially in the compressed, final condition which is a stretch condition. So initially x1 is equal to minus x, and in the stretch condition your x2 is equal to positive x. So the final condition which is your stretch condition, and in the stretch condition x2 is equal to x. Then the work done will be W is equal to minus k from minus x to x dx. So it is nothing but if you integrate this, and with putting this value from minus x to x, we are just putting this value from minus x to x, you get here, you get total work done is nothing but the 0. Here you get this total work done which is nothing but 0. It means that in the first, basically here we can see in the initially the spring is in the compressed state, second or final state the spring in the stretch condition, x1 is minus 1, x2 is x. If you integrate this, you get the total work done which is equal to 0. So here we are take or just study the 5 conditions, or here we can calculate this work done with a varying force. In the first conditions, your x1 and x2, x1 at the natural state, x2 which is in the stretch condition. Okay, first natural state, in the second final which is stretch, you get the work done minus 1/2 kx square. Second again natural state and compressed state, again in the second condition you get minus 1/2 kx square. In the third case we see that first condition is a stretch condition, so x1 is equal to x and x2 is equal to, which is at the natural condition, so x2 is equal to 0, you get total work done is equal to 1/2 kx square. In your fourth condition, so this is initial condition is compressed, so x1 is equal to minus 1, second final condition is a natural state, in that natural state x2 is equal to 0. So by using all these points or considering all the various cases, we determine the work done for the varying force.